Welcome back to The Explainer. Today, we're taking a highly structured analytical look at a genuinely fascinating piece of technical documentation, the Merg-E language specification. If you've been following the latest developments in decentralized infrastructure, you've probably caught wind of this project. We're going to break down exactly how this language is built, pulling directly from the developer specification posts.
But right up front, I want to establish our roadmap. This explainer is actually part one of a 6-part series mapping out the entire Merg-E language specification. Today, we're focusing strictly on the top-level overview and the subjects covered in the first 3 posts of the spec. Each of the remaining 5 explainers will then center on the material of 4 posts at a time. We aren't here to oversell the language or, guess its future adoption. Our goal is just to deliver grounded, structured facts about how Merg-E is designed to work, based purely on the source material.
So, let's kick things off with a clear definition. What actually is Merg-E? Well, it's a highly opinionated domain-specific language, or DSL. It's really not trying to be a general-purpose tool like Python or C++. Instead, it's got a very narrow, specific use case, writing Web 3.0 bots and Layer 2 nodes. That's it. And its entire architecture revolves around a really strict adherence to the least authority principle, meaning components are only ever given the absolute bare minimum permissions they need to function. Here is our blueprint for today. 1. Merg-E overview. 2. The least authority philosophy. 3. Files, scoping, and names. 4. Documenting with reverse markdown. And 5. Actors and actor pools. Let's dive in.
Okay, part 1, Merg-E overview. Let's talk about this practical merge.
So, the name Merg-E isn't just some random label they slapped on. The documentation explicitly describes it as a practical merge of a few different programming paradigms. It pulls a little bit from pure object capabilities, the actor model, data flow architectures, and functional programming. And it's practical because it's designed with some very strict time resource constraints in mind. Oh, and the E in the name? That's a direct tribute to the classic E programming language, which pioneered a lot of these distributed object capability concepts. As the creator puts it, Merg-E is like E, mostly in spirit.
Moving right along to part 2, the least authority philosophy. Let's look at the security backbone. This lays out the deliberate compromises and the hard design rules of the language. First off, Merg-E leans heavily on directed acyclic graphs, or DAGs. You actually won't find traditional structs or dictionaries here. Basically, if a DAG can do the job, use a DAG. Second, it uses thin abstractions. This purposefully exposes the internal mechanics of the language to keep the implementation really small. Third, we have move as default ownership. This means if you capture a standard mutable variable, you literally steal ownership from the parent scope, a concept heavily inspired by the old C++ auto_p. But the most defining trait? Making the safest options the easiest to type. Taking a cue from the cryptography library libsodium, Merg-E guarantees that safe code is clean to write, while dangerous or shared code requires really verbose, explicit typing. It literally makes the programmer stop and think.
Now, because of those incredibly strict rules, the language needs a pressure valve. Enter the hazardous modifier. This is an explicit, highly auditable escape hatch. If a programmer absolutely has to bypass a strict security rule, say using a blocker inside a lock or doing a risky typecast, they are forced to label that block as hazardous. And get this, by default, the compiler will actually throw an error if it sees this. To actually get it to compile, you have to pass a very specific compiler flag, jokingly named Trust Me Bro. It tells the compiler, look, I know this violates the rules, but I know what I'm doing. It's a pretty brilliant way to make security compromises glaringly obvious during a code review.
All right, part 3, files, scoping, and names. Let's get into the structural elements. When you're structuring a program in this DSL, you're only dealing with 2 super simple file types. On the left, we've got .mrg files. Those are your main program files. And on the right, .mrm files, which are your module files. And that's it. There is a deliberate lack of any complex directory or packaging system. Because it's meant for specialized Web 3.0 bots, it just completely avoids the heavy, complicated packaging structures you'd normally see in a general-purpose language. Now, what's really wild about this structural design is the extreme minimalism of the language's reserved vocabulary. Merg literally only has 2 reserved keywords in the entire language: scope and resolve order. 2. The designers did this specifically to prevent keyword bloat so developers don't constantly run into naming conflicts with their own variables. Now, While MIP manipulating resolve order directly is definitely considered an advanced maneuver, having this dual keyword design gives a massive amount of flexibility for the language's internal semantic lexer to manage authority flex.
Let's jump to part 4, documenting with reverse markdown.
So Merg-E handles comments and documentation through a system it calls reverse markdown. Instead of your standard comment blocks, developers use 4 backticks followed by the word implod doc, and then they just write standard markdown directly inside the code. It keeps the visual formatting totally raw, very direct, and incredibly easy to parse for automated documentation generators. It's a perfect fit for that thin abstraction philosophy we talked about earlier.
Finally, part 5, actors and actor pools. Let's look at concurrency in Merg-E. Concurrency here revolves entirely around the actor model. And what's fascinating is that initially there is zero syntactical difference between a standard ephemeral function and a persistent actor. You literally write the exact same block of code. To turn that standard function into an actor, you just prepend it with the lang.callable.actor modifier, or you can just type actor for short.
But adding that tiny modifier fundamentally changes what happens under the hood. Let's walk through this quick comparison. With a normal non-actor callable, a brand new scope and state are created every single time you call it. Plus, consecutive calls might actually run in parallel. But with an actor, the scope and the state persist across multiple calls. Its execution gets locked to a single scope, and crucially, consecutive calls to that specific actor will always run in sequence, never in parallel.
Because an actor's scope persists like that, the source material highlights a massive warning regarding memory and ownership. The crucial takeaway is this. If you explicitly borrow a mutable variable from the outer closure into an actor, that borrow is bound to the actor's scope. And since an actor can live for the entire lifetime of the application, that borrowed mutable might literally never be given back. Developers have to be incredibly careful with how they pass data into these long-lived structures.
Now, naturally, because a single actor processes tasks sequentially, it can easily become a bottleneck. So, to improve parallelism without breaking the actor model, developers can use this specific notation, : and angle brackets, to instantiate an actor pool. What this does is create a collection of identical actors that all share a single internal message box. When you invoke the pool, the runtime just automatically distributes the work among the idle actors in a round-robin fashion. It's a super clean way to safely scale up your concurrency.
So we've covered the macro philosophy, the simple files, the strict least authority rules, and the bare basics of actors. But what happens when your task execution needs get significantly more complex? What happens when you suddenly need semantic locks? Or when tasks need to yield the CPU at specific continuation points just to keep the whole system responsive? Well, that is exactly what we're going to explore in part 2 of this series. Thanks for joining me on The Explainer, and I'll see you in the next one.